So far we've been talking about the legend symbol. Now the legend symbol has a problem. The problem is that it is valid only when p is a prime number. Now it can be used to check whether a number is a quadratic residue mod p only when p is a prime number. Now in case p is not a prime number, we cannot make use of the legend symbol. Therefore we go for what is called the Jacobi symbol. Now coming to the definition. If p is a positive odd integer with prime factorization, p is equal to product pi raised to alpha I, where I ranges from 1 to r, then the Jacobi symbol NOP is defined for all integers n by the equation NOP is equal to product of NOPI raised to alpha I, where I ranges from 1 to r, and NOPI is the legend symbol. We define NO1 as 1. Now the possible values of NOP are 1, -1 or 0, with NOP is equal to 0 if and only if the n and p are not relatively prime. Now most of the properties of the Jacobi symbol carry over from the properties of the legend symbol. Anyway, let's prove them. So the first theorem in this section says that if p and q are odd positive integers, we have MOP into NOP is equal to MNOP. That is, the multiplicative property holds. Number 2, NOP into NOQ is equal to NOPQ. Number 3, MOP is equal to NOP whenever m is congruent to n mod p. And 4, A squared NOP is equal to NOP whenever the GCD of A and P is equal to 1. Now let me prove that. Suppose P can be written as product of pi raised to alpha I, where I ranges from 1 to r. Now we know that the legend symbol is multiplicative. Therefore, I take the left hand side of that property and say MOP into NOP can be written in terms of the definition as product of MOPI raised to alpha I, product of NOPI raised to alpha I, which can be in turn written as product of MOPI into NOPI the whole raised to alpha I. Now because of the multiplicative nature of the legend symbol, I can write this as product of Mn over Pi raised to alpha I, and this by definition is equal to Mn over P. So that proves the first result. Now coming to the second result, again we take the left hand side. So before that we define P and Q a little differently. I assume P is equal to Pi raised to alpha I into product Rk raised to gamma k, and Q is product of Qj raised to beta j into product Rk raised to delta k with appropriate limits. Now I can write PQ as product of Pi raised to alpha I, product of Qj raised to beta j, product of Rk raised to gamma k plus delta k. Now NOP into NOQ, which is the left hand side of that property, as usual I write it in terms of the definition. So I get this NOPI raised to alpha I, NORK raised to gamma k, NOQJ raised to beta j, NORK raised to delta k. Now rearranging this, I get NOPI raised to alpha I, product of NOQJ raised to beta j, product of NORK raised to gamma k plus delta k. Now by definition this is equal to N over PQ. Now let's come to the third property. If m is congruent to n mod p, then I know that m is congruent to n mod pi for each I, and hence m over p is equal to product of m over pi raised to alpha I, which is equal to product of NOPI raised to alpha I, which again according to definition is equal to n over p. Coming to the fourth property, we have a squared n over p is equal to a over p the whole squared into n over p. Now I know that a over p is going to be either plus or minus 1. Why? Because a and p are relatively prime, and if a and p are relatively prime, it cannot be A over p cannot be 0, and therefore plus some this can be written as a square NOP can be written as plus or minus 1 the whole squared into NOP, which gives me NOP. Now coming to the next theorem. Again this follows from the properties of the Legendre symbol. Anyway, again let's prove that minus 1 over p is equal to minus 1 raised to p minus 1 by 2, and 2 over p is equal to minus 1 raised to p squared minus 1 by 8. Now I write p as p1 p2 up to pm, where the factors pi are not necessarily distinct. Then I can write p as product I equal to 1 to m of pi, and this I can write as 1 plus pi minus 1, product of that, where I ranges from 1 to m. Now multiplying this out, I get 1 plus summation I equal to 1 to m pi minus 1 into summation I not equal to j of pi minus 1 into pj minus 1, and so on. Next term will have term will have 3 factors, the next will have 4, and so on. Now I know that each of these pi minus 1 terms is each pi minus 1 is an even number because pi is odd, and therefore the this term is even. The pi summation I equal to 1 to m pi minus 1 is even. The next term is divisible by 4, the next term is divisible by 8, and so on. Now I reduce this modulo 4, and so all the terms except the 1 plus sigma pi minus 1 become 0, and so I get p is congruent to 1 plus summation I equal to 1 to m pi minus 1 mod 4, and therefore minus 1 raised to p minus 1 over p is equal to product of minus 1 over pi. Now this I can write as minus 1 raised to sum of pi minus 1 by 2, and this is equal to minus 1 raised to p minus 1 by 2, which proves 1. Now if I want to prove 2, it's quite similar. I write p squared as 1 plus pi squared minus 1. Same as we did earlier, we get something like this. Now I know that each of these terms pi squared minus 1 is divisible by 8, and so we have p squared is congruent to 1 plus summation I equal to 1 to m pi squared minus 1 mod 64, and therefore 1 by 8 into p squared minus 1 is equal to summation 1 by 8 pi squared minus 1 mod 8. This is also true mod 2, and therefore 2 over p is equal to product I equal to 1 to m minus 1 raised to pi squared minus 1 by 8, which is equal to minus 1 raised to p squared minus 1 by 8. Now we will prove one more result, the reciprocity law for Jacobi symbols. If p and q are positive integers with p and q with the GCD of p and q equal to 1, then p over q into q over p is equal to minus 1 raised to p minus 1 into q minus 1 by 4. Now again I am going to take p as p1 p2 up to pm, q as q1 q2 up to qn, where pi's and the qj's are primes. Then pq into q, p over q into q over p can be written as product of I equal to 1 to m, product of j equal to 1 to n, pi over qj into qj over pi. Now this is equal to minus 1 raised to r, where r is equal to summation I equal to 1 to m, summation j equal to 1 to n, 1 by 2 into pi minus 1 into 1 by 2 qj minus 1. Now this I can write as 1 by 2 into pi minus 1 into summation 1 by 2 into qj minus 1. But we just proved in the previous theorem that the summation 1 by 2 into pi minus 1 is 1 by 2 into p minus 1 mod 2, and similarly summation I equal to 1 to m, 1 by 2 into qj minus 1 is 1 by 2 into q minus 1 mod 2, and therefore r is equal to 1 by 2 into p minus 1 into 1 by 2 into q minus 1 mod 2. Again, let me do one small example. We want to determine whether 888 is a quadratic residue or non-residue of the prime 1999. So we find 888 over 1999. So 888 I can factorize it as 2 squared into 2 into 111 over 1999. Now 2 squared, a squared over n over p is equal to n over p. So this becomes 1. 2 over 1999, using the previous theorem, the 2 over p is equal to p squared minus 1 over 8. Using that, this again is 1. So this is equal to 1111 over 1999. Now using quadratic reciprocity, I can write this as 1111 over 1999 is equal to minus 1 raised to this into 1999 by 111. Now when I simplify this, I get minus 1 into 1 by 1111. Again, this is equal to, this I know is equal to 1, so therefore I get minus 1. Therefore 888 is a quadratic non-residue of 1999. One more example to determine whether minus 104 is a quadratic residue or non-residue of the prime 997. We find the Jacobi symbol minus 104 over 997. As usual, we factorize it, and from theorem 10 and using quadratic reciprocity, I get this 4 over 997 is 1, 2 over 997 is 1, minus 1 over 997 is when I simplify all this, I get minus 13 over 997, which is equal to minus 997 over 13, which is equal to minus 9 over 13, which is equal to minus 1. Therefore minus 104 is a quadratic non-residue of 997.